When a capacitor bank is switched on, a transient current surge occurs. This is primarily due to the initial charge state of the capacitor bank. Initially, the capacitor bank is uncharged. When it is connected to a voltage source, it rapidly charges. This sudden inrush of current causes a voltage drop across the bank's internal resistance, contributing to the oscillating transient. Another key factor is the formation of a resonant circuit. The capacitor bank forms a resonant circuit with the inherent inductance of the power system. The natural frequency of the circuit is determined by the capacitance and inductance values. When the capacitor bank is switched on, the circuit resonates, producing an oscillating current. The frequency of the oscillation is approximately equal to the resonant frequency of the circuit. Furthermore, overcharging and discharging phenomena contribute to the transient. The capacitor bank charges rapidly at first. However, as it approaches its maximum voltage, the current starts to decrease. Due to the inductance in the circuit, the current continues to flow, slightly overcharging the capacitor. This overcharging leads to a reversal of current, causing the capacitor to discharge. This cyclical process of overcharging and discharging sustains the oscillation. Capacitors typically oppose rapid voltage changes by storing charge. However, during the initial transient, the capacitors are not initially charged. Therefore, they do not immediately oppose the voltage change, allowing for a rapid surge of current. During the transient, the capacitor bank's impedance changes rapidly. At the start of charging, the impedance is low, being primarily capacitive, allowing high currents to flow. As the capacitor charges, its impedance increases, becoming more inductive, which limits the current flow. The oscillating transient gradually dampens due to several factors. Firstly, circuit resistance dissipates energy, reducing the oscillation amplitude. The resistance inherent in the conductors, connections, and internal components of the capacitor bank and the power system acts as a damping force. Secondly, current-limiting devices can be added to the circuit to limit the current surge and reduce the transient severity. These devices may include resistors or reactors. The oscillating transient caused by switching on capacitor banks is a common phenomenon in power systems. It can cause voltage fluctuations, equipment damage, and other disturbances. Therefore, proper design and protective measures are necessary to minimize the impact of these transients. Let's delve deeper into the concept of resonance and its role in creating oscillating transients when switching capacitor banks. Resonance occurs in a circuit when the inductive reactance and capacitive reactance are equal. Inductive reactance is the opposition to current flow offered by an inductor, while capacitive reactance is the opposition to current flow offered by a capacitor. When these reactances are equal, the circuit is said to be in resonance, and the impedance of the circuit is at its minimum. In a power system, inductance is primarily associated with transmission lines, transformers, and motors, while capacitance is often introduced by capacitor banks used for power factor correction. When a capacitor bank is switched on, it introduces a sudden change in capacitance to the system. This change in capacitance interacts with the existing inductance, potentially creating a resonant circuit. The resonant frequency of this circuit is determined by the formula F equals 1 divided by 2 pi times the square root of L times C, where F is the resonant frequency, L is the inductance, and C is the capacitance. At the resonant frequency, even a small amount of excitation, such as the switching transient, can cause a large oscillation in current and voltage. This oscillation is the oscillating transient that we observe. The severity of the transient depends on several factors, including the magnitude of the switch capacitance, the system inductance, the system impedance, and the switching instant and the voltage waveform. Switching at the voltage peak can cause the largest transient. The initial current surge associated with switching on a capacitor bank can be several times the rated current of the capacitor bank. This high current can stress circuit breakers, switches, and other electrical equipment. Furthermore, the oscillating voltage can cause insulation breakdown and damage to sensitive electronic devices. To mitigate the effects of these transients, several techniques are employed. One common technique is to use pre-insertion resistors or inductors. These devices are temporarily inserted into the circuit during the switching operation to limit the inrush current and dampen the oscillations. After a short period, they are bypassed and the capacitor bank is fully connected to the system. Another technique is to use controlled switching devices. These devices allow the capacitor bank to be switched on at a specific point in the voltage waveform, minimizing the transient. For example, switching at the voltage 0 crossing can significantly reduce the inrush current. Furthermore, harmonic filters can be used to reduce the harmonic content of the transient. These filters are designed to attenuate specific frequencies that are likely to be excited by the switching transient. In addition to these techniques, proper system design and grounding practices are essential for mitigating transients. A well-designed system will have adequate insulation, surge protection devices, and grounding to protect equipment from damage. Now, let's consider the role of damping in mitigating oscillating transients. Damping refers to the dissipation of energy from the oscillating circuit, which reduces the amplitude of the oscillations over time. Several factors contribute to damping in a power system. The resistance of the conductors, transformers, and other electrical equipment provides inherent damping. This resistance dissipates energy in the form of heat, reducing the amplitude of the oscillations. In addition to inherent resistance, damping resistors can be intentionally added to the circuit to increase the damping effect. These resistors are typically connected in series with the capacitor bank or in parallel with the inductor. The value of the damping resistor is chosen to provide the desired level of damping. The effect of damping can be quantified by the damping ratio, which is a dimensionless parameter that indicates the rate at which the oscillations decay. A damping ratio of 0 corresponds to no damping, while a damping ratio of 1 corresponds to critical damping, where the oscillations decay as quickly as possible without any overshoot. A damping ratio greater than 1 corresponds to overdamping, where the oscillations decay slowly without any overshoot. In practical power systems, a damping ratio between 0.1 and 0.5 is typically desired to provide adequate damping without significantly reducing the efficiency of the system. The choice of damping method and the value of the damping components depend on the specific characteristics of the power system and the severity of the transients. Careful analysis and simulation are often required to determine the optimal damping strategy. Now let's talk more about capacitor impedance during transients. The impedance of a capacitor is frequency dependent. It is given by the formula Z equals 1 divided by j omega c, where Z is the impedance, J is the imaginary unit, omega is the angular frequency, and C is the capacitance. At low frequencies, the impedance of a capacitor is high, while at high frequencies, the impedance is low. During a transient, the frequency content of the voltage and current waveforms is broad, ranging from the fundamental frequency to high-frequency harmonics. At the start of the transient, the high-frequency components dominate, and the capacitor bank's impedance is low. This low impedance allows for a large immersed current to flow. As the capacitor charges, the voltage across the capacitor increases, and the current decreases. As the current decreases, the high-frequency components diminish, and the lower frequency components become more dominant. As the frequency decreases, the capacitor's impedance increases, limiting the current flow. The changing impedance of the capacitor bank during the transient contributes to the oscillating nature of the current and voltage waveforms. The interaction between the capacitor's changing impedance and the system inductance creates a complex interplay that can lead to sustained oscillations. Therefore, understanding the frequency-dependent impedance of capacitors is crucial for analyzing and mitigating transients in power systems. It is important to consider the practical implications of oscillating transients in power systems. These transients can have a significant impact on the reliability and performance of electrical equipment. Voltage fluctuations caused by transients can disrupt the operation of sensitive electronic devices, leading to malfunctions or data loss. High current surges can overheat conductors and damage circuit breakers, switches, and other electrical components. Furthermore, the oscillating voltage can stress insulation and lead to insulation breakdown, causing short circuits and equipment failure. To protect equipment from damage, surge protection devices, such as surge arresters and transient voltage suppressors, are commonly used. These devices are designed to limit the voltage across sensitive equipment during a transient, diverting the excess current to ground. Surge arresters are typically installed at the service entrance of a facility to protect the entire electrical system from incoming surges. Transient voltage suppressors are typically installed at individual equipment locations to protect specific devices. In addition to surge protection devices, proper grounding practices are essential for mitigating transients. A well-designed grounding system provides a low-impedance path for fault currents to flow to ground, minimizing the voltage rise during a transient. The grounding system should be designed to comply with applicable codes and standards, such as the National Electrical Code Section 250. Regular inspection and maintenance of the grounding system are essential to ensure its effectiveness. Another important consideration is the coordination of protective devices. Protective devices, such as circuit breakers and fuses, should be coordinated to ensure that the device closest to the fault clears the fault quickly, minimizing the impact on the rest of the system. Coordination studies are typically performed to determine the optimal settings for protective devices. In conclusion, oscillating transients caused by switching on capacitor banks are a common phenomenon in power systems that can have significant impacts on equipment reliability and performance. Understanding the underlying causes of these transients and implementing appropriate mitigation techniques is essential for ensuring the safe and reliable operation of electrical systems. This includes proper system design, surge protection, grounding practices, and coordination of protective devices.